Hi everyone, this is Hector, your AFM expert on nanosurf. Do you know how fast glass degrades? Glass degrades through four different mechanisms. Scratches that typically appear when you touch the glass with something that is harder than the glass. Leaching, which is the glass turning whitish and not very transparent. Grizzling, which is development of small miniature cracks which can grow with time. And the formation of patina is when the degradation on the surface of the glass remains on the surface of the glass and make it not transparent. We're going to try to reproduce some of these effects here in the lab, and we're going to try to see them with the AFM. So let's follow me into the lab. In order to better understand this Friday AFM experiment, I need to explain a little bit what is glass. You see, the main component of glass is called silica, and silica is made of one silicon atom surrounded by four oxygen atoms. Silica itself tends to form crystals with perfectly oriented units. The problem is that this is too brittle for human applications. But lucky for us, silica also form glass, which has the same components, but this time they are not perfectly oriented. They are randomly oriented. Thanks to this random orientation of the silica units, now the material is stronger and has a higher melting point. However, this is still not good enough. But then we are lucky again, because we discovered that if we introduce some ions into the glass, some sodium or some calcium, then we obtain something called a soda lime silica glass. This type of glass is now good enough for making bottles or glasses or even some recipients for chemical reactions. And yet, we were lucky again another time, because we discovered that if we replace some of these ions for a boron, we obtain something called a borosilicate glass, which is even stronger and even more heat resistance, to the point that this glass can be used for cooking. Now the question is, does glass ages? And in order to answer this question, we need to see what happens to glass when we put it in contact with a solution. You see, when glass is in contact with a solution, it forms a layer called the hydration layer. This is where the solution starts to penetrate inside of the glass. And when the solution penetrates inside of the glass, it starts to react or interact more precisely with the ions in the glass. And the ions now are free from the glass. And when the ions become free from the glass, particles of silica also break from the glass. This combination of ions and silica particles form a layer on top of the hydration called the gel layer, which is very loosely attached particles. Because the ions are much lighter than the silica particles, they move farther away, and eventually they go away from the surface. But the silica particles, being more heavy and large, they remain close to where they were initially generated. Some of them redeposit or reattach to the glass, ultimately forming a kind of crater structures. If the glass has a low ion concentration, like for instance the borosilicate glass, this process can stop because the hydration layer can no longer reach more ions. In glasses where the ion concentration is larger, this process really never stops, because the hydration layer, as it fits more into the glass, can reach more ions and continue this process, degrading the glass, making the surface more rough, and eventually creating cracks that can break the glass apart. This process is usually called creasing, and it tends to happen with soda lime rich glasses. Since we are discussing this, we need to discuss also another scenario where the solution suddenly becomes more rich in ions and silica particles. If this happens, maybe because somewhere else in the solution there is another piece of glass degrading very fast. If this happens, what occurs is that new layers of silica attach on top of the surface of the glass. These new layers increase the thickness of the glass, and in principle, they can have different structures depending how fast they deposit, and even different ions. So they can have different colors and mechanical properties. And also, it's possible that these layers act like tiny mirrors, creating optical effects. This is usually referred as the patina. So these are the samples we're going to be looking at today. We have a Friedrich vase from the 70s, a brand new champagne flute, a glass candlestick holder, also brand new, and a borosilicate glass slide. The microscope glass slide we know for sure is borosilicate. I am not so sure about the flute and the candlestick holder. It could be really anything, but I hope that because they were really cheap, this will be a soda lime glass. The Friedrich base, this I'm pretty sure is a soda lime because it's from the 60s. And it's a glass that was blown and it has bubbles inside, meaning that it has a low melting point. So probably it was produced with soda lime. Interestingly, if we look at how glass obtains the colors, this also means that very likely this glass has gold particles on it, or copper, or even selenium particles. All of these probably gonna interact very nicely with acid. So I'm betting that the Friedrich glass will be the most interesting one. And of course, the first part is the most fun part of the project, which is breaking the glass into pieces. Some of you might remember that this is not the first time we image glass in Friday AFM. Some time ago, we looked at how different cleaning processes affect glass. And we got glass slides, which I clean with alcohol. I clean them with dishwasher, and also I use a window cleaner. And from all these processes, I was not very satisfied because all of them leave residues. But I came to the conclusion that combining all of them, sometimes you might get a decent result. Because I was not exactly happy with this result, sometime later I did another experiment, another Friday AFM, where I look at the effect on water coating or water protection from using peroxide and different coating agents that you can find in Amazon. And I like the effect of peroxide, that to me was the best product for cleaning glass, at least when it comes to removing organic compounds. Maybe peroxide and isopropanol, and using of a soft tissue for drying out. And this is exactly the process I'm going to follow here. I'm going to use hydrogen peroxide, some isopropanol, and a tissue for drying it out. By the way, something that I couldn't share at the time, and I can share with you now, is that when I try the different water protection materials, I did some tests on my kitchen. Um, and here you can see on, I think I remember on the left was peroxide, and on the right was um, the water protection material for cars. The next thing I needed to decide was the aging procedure. Naively, initially I thought that I can just dishwash some of these glasses many times and then record the degradation over time. Because many times I went to restaurants and I saw that they have very degraded glasses. But this didn't work. After somewhere between 50 and 100 washes with the dishwasher, I still couldn't see any degradation. So I give up on this. Then I wanted to produce the degradation with common household items, just in case if you want to reproduce it to make it easy for you. And looking at the different products that we can use, I decided to go for a vinegar and lemon juice. So I bought a lot of lemons and started, and I put the glass on lemon juice for a while. I didn't saw any results here either, so I give up on these solutions, and I went for nitric acid. Nitric acid is basically the equivalent of having something called soft water, which is water that is very acid. It's not exactly the same, but it's somehow equivalent to speeding up having the glass in this type of water for many centuries. For the imaging part, I'm going to use wave mode, which has low lateral forces and will preserve the tip and the structures in the surface. For this probe, 15 kilohertz is a nice wave mode frequency, and I start by calibrating the probe because in this way I can know exactly the force that I'm applying and also the amplitude of the oscillation. Yeah, hit apply. And I want about 25 nanometers of oscillation, but before adjusting lasers, before adjusting the laser intensity, I'm going to adjust the laser position. And here I look at the cell controller ring, which is basically the interaction amplitude, and I'm going to try to minimize it. Yeah. We need to calibrate again because any movement of the lasers means that we lose the calibration. I forgot to apply. Okay, then I'll put a little bit of AC amplitude to reach the 25 nanometers. Yeah, that should be enough. And now I put a set point of 900 piconewtons because from my experience, this value is good enough to get the surface topography, but it's low enough to preserve the tip. While it's approaching, I'll select the scanning parameters. Yeah, 2 micrometers. I think we can do 2 hertz line rate. We can start with 256 points per line. Sometimes during the approach, it's possible to get a false approach if the tip, if the probe starts bending due to electrostatic interaction with the surface. Approach is done. Let's check if it is indeed approached. Yes, we can see that when the PSO stands, the interaction curve changes, so we update it. And in this case, I updated at 20 nanometers from the surface because there is no reason for updating it farther away, and the closer we are, the better. One way of checking what is the good gain is by looking at the cell controller in, and if you see if I put it too high, it starts to oscillate. So by looking at that graph, I can find the right gain for the scan. Yeah, just click start. And then here we can see the surface of the microscope glass slide, and it's full of craters. As we mentioned before, the borosilicate glass typically is passivated by putting it in acid to create this gel layer, which eventually develops into craters, which eventually develops in a passivated layer to prevent the hydration layer to reach ions in the glass and continue the degradation. Out of curiosity, I measure the size of these craters, and yeah, it's about 180, maybe 200 nanometers, or even smaller. I can anticipate to you now that this is quite interesting because in other classes we will see craters of different sizes. This probably has to do with the ordering on the silica glass and the amount of ions, but I don't have any data to support this. It's just based on very small experimental evidence. And there you have it, white mode imaging on glass. It's possible to optimize a few things here. For instance, we can scan faster. I think we can easily obtain 4 hertz, but this of course depends on the quality that you want for the final image. If you want every single line to match the trace and retrace, or if you're tolerant to some inaccuracies. Also depends on the height of the structures we're going to find. Most of them are quite small, but now and then there is large structures that they go really high. If we want to go faster, we can increase the frequency of the wave mode. But I like these parameters, and I really don't mind taking a little bit longer to capture the data. In terms of set point, it's still okay to apply a little bit more force. Doing tests, I went up to 2, 3, 4 nanonewtons, and I didn't notice tip degradation. But I was only after 1 or 2 images. Of course, if you want to take a lot of images or scan a large area, probably you want to keep a low set point. Here are the results. The microscope glass slide, as we saw before when imaging, is covering craters made of silica. This is a passivation treatment where they put the glass slides in acid to create this silica layer that is protected or protects the glass from further degradation. We can see here that the cleaning procedure with the peroxide and the tissue doesn't affect the surface, doesn't modify it, or more importantly, doesn't add more dirt to it. After using the nitric acid for 12 hours, I didn't saw any change, which in a way is good. It confirms that this treatment protects the glass. This other one is the candlestick holder, which was a surprise to me because I was expecting here very cheap glass. I was not expecting a treated glass, but as you can see, the glass is full of craters. So this was probably treated with acid to make it last longer, to have better quality glass. One thing that I noticed is that when I zoom out, I found these very large structures, and I couldn't figure out what they are. The only thing I noticed is that after the nitric acid treatment, they were not there anymore. But we can see that before, some of them were missing. We can see some residue from where they were. So this makes me believe that these are just calcite deposit, not native of the glass, but a result of cleaning or treatment they did. And by the way, this glass as well doesn't get affected by the nitric acid. We can see the same structures before and after the treatment, which is good. Here, just to show you the different scales, if you really look closer, you should be able to see the small craters, but you also see the big calcite deposits as a comparison of the size of one against the other. And this is the flute. The flute was a little bit of a puzzle to me at the beginning because I image and I almost see craters, but not really. I thought the cleaning was not very good, so I wash it again and I still don't see the craters. Sometimes I can almost guess where they are. And then I put it into acid. And the craters were a little bit more visible. It's still not very good, and I thought that I mess up with the cleaning, or at some point maybe I touched the glass with my finger, until I zoom out. And when I zoom out, I saw big craters. I see this semicircular structure, and I figured out what was going on. So here, there was some sort of protective layer, which I'm not sure what it is. Could be a layer of silica, could be a layer of some polymer. But what happens is that when I put it again into acid, and now for 12 hours, this coating layer starts to degrade. And there were areas where it got removed completely when I was cleaning with the tissue. You can see here in the cross section that the thickness of this layer is, I don't know, maybe around 5 nanometers, no more than that. Last but not least, we have the Frederick glass. This I found it in a flea market. Well, I don't know the story, but this thing was out for since the 60s, so it accumulated a lot of contamination, dirty scratches. So I watched it a couple of times, but still I was seeing an image that was covered in contamination. So I thought I was not going to be able to get anything out of this. But then I put it into acid for 12 hours, and I start seeing craters. They are very faint, but they are there. You can see a couple of them in the bottom image. So I decided to repeat the process, put it for another 12 hours. What happened to my surprise is that suddenly all the contamination that was everywhere dropped, and I could see craters everywhere, which I definitely couldn't see before, meaning that this has to be soda lime glass, as I thought, and meaning that here we are able to see the degradation process, which is really, really nice. Hope you like our little experiment today. The message to take home is that the glass degrades. However, don't expect the glasses in your houses to fall apart into pieces because this process takes centuries. But with the use of an AFM, we are sensitive enough to see this degradation even after a few hours with an acid treatment. Hope to see you on our next experiment. Bye. I almost forgot. And the oldest artificial glass is an Egyptian faience statue, which has a glass coating on it, and is 34 centuries old. There are bits that are older than this, but there is more uncertainty on the age of these ones. And of course, there is silex axes and knives, but these are not artificial glass. This is naturally occurring glass that was shaped in the form of tools. So there you go. You know how long glass lasts, and now you know more of why glass degrades. Hope you like it.